I love about BrainMind is that it's so cross-disciplinary, not just between the different fields of science, but also between scientists and entrepreneurs and technologists. But you, even as an academic and a clinician, have diverse interests. They've even made you an honorary professor of engineering at Stanford. So maybe talk to me a little bit about what has given you the interest to pursue something. You obviously went through med school, you became a neurosurgeon, a professor of ophthalmology.
Not medical school. I actually have a PhD in
interesting.
neuroscience, and I studied mathematics and I studied economics, and I began PhD programs in both of those as well. So I have a varied background. I've spent some time working in a startup company and some other stuff. But I come to the field of sight restoration as a vision scientist and as a neuroscientist. And so my interest is in taking what we've learned scientifically about the visual system and how seeing works, and using that to develop technologies to restore sight. And this turns out to be a fundamentally very interdisciplinary venture. Even, as you said, within the field of science itself, it requires a mixture of vision science expertise, surgery, neuroscience, neurophysiology, electrical engineering, signal processing, materials science, and so on. And I find that incredibly exciting to be involved in, to be on the steep side of the learning curve in all these different areas simultaneously, so that we can tackle one problem that has to do with sight restoration.
And do you feel like Stanford has played a role in that? I know you did your undergrad and PhD at Stanford and collaborated in the past with Ed Boyden, who I know invented optogenetics there with Caldiceroth, and that is also another very cross-disciplinary breakthrough. Is there something in the water there at Stanford that makes different departments work together?
That's a great question, and I love that question. I actually love Stanford University very much. I was a PhD student and a postdoc there, and I returned there with great joy, actually almost 10 years ago to the day, because of that. I think what's in the water is the spirit of possibility, of doing things that previously were thought to be out of the realm of what we can do. But the sky's always the limit at Stanford. For some reason I don't quite understand, but it's fantastic.
This breakthrough that you're working on is something that literally was science fiction. It was in Star Trek, where a blind man had sight restored to him with a visor. And that is a vision for the future. But it seemed like science fiction because there was so much challenge in translating what are actually the signals that make us see. So is that what your work has been investigating?
Very much so. So I moved into this field of sight restoration coming from basic neuroscience research and studying how the retina normally works to initiate the process of vision, of seeing. And the neuroscience of how the retina works, as you'll hear in my talk tomorrow, is actually quite advanced. We know a lot about how the retina works. We're not done figuring it all out. There are still aspects of the circuitry we're trying to understand and so on, but we know a lot. And we know a lot more about how the retina works, for example, than any other part of the brain. By a country mile. We actually really are starting to get it about what the circuitry is, what the cell types are, what the signals are, how that mediates the process.
Which is interesting because they're also a form of neurons.
Yes, very much. No, they're not a form of neurons. They're neurons, straight up. And
so what makes them easier what makes it easier to understand the process then?
It really technical matters, such as the fact that it's easily accessible, that people have been able to study the retina by looking at it through the eye, by approaching it, using electrodes through the eye. It's just close to the surface and accessible. And because of that, all the way since more than 100 years ago, people have been able to study the retina in a way that they weren't yet able to study the brain. So one way to think of it, I like to say, is that our understanding of the brain is always like 30 years behind the retina. We figured out how to do things in the retina, how to measure things, how to sort out how it works, and then 30 years later, people working in the brain catch up. Not because they're less smart, they're just as smart, but it's just harder to figure out how the brain works. The techniques and the advances have allowed us to understand the retina in a deep way. And what I find most invigorating and exciting about it is that if we understand that well, how it works, shouldn't we be able to build something that does the same thing? Shouldn't we be able to restore the function of a retina that no longer works properly? Shouldn't we be able to construct electronics and materials that interface to the retina and restore some aspect of its function that it has lost? We should, because if all of this investigative science and exploratory science is worth something, to me, It's that the knowledge we acquire, at some point the rubber meets the road with that knowledge, and it allows us to do things that we weren't able to do before. It allows us to solve problems for humanity. I really deeply think that restoring sight through replacing the retina with electronic devices, it's absolutely an idea whose time has come. We're not the first people to have that idea. Lots of people have had that idea all the way going back to sci-fi. But it's not sci-fi anymore. It's just straight up sci. We're in a place where it's time to just do it, and I think we can.
What has made it become straight up sci? You are on the cutting edge. I think people watching are probably going to be very interested to hear what has changed in the last 2 years. You're seeing these tools, you're using these tools in your lab. What new tools are available that are enabling you to unlock things today that weren't possible 3 years ago?
I wouldn't say it's the last 2 years that have made all the change. I would say it's more like the last decade, where we've started to put together information from many types of studies, including studies in my own lab with large-scale neurophysiological investigations of retinal function, where we can see that what's actually going on is that the retina is far from being a simple pixel detector or camera device. It's nothing like that. It's actually a complex neural circuit consisting of many different cell types that perform different functions, connect up to one another in particular ways, and send different types of visual information to different targets in the brain. This clarity that has emerged scientifically tells us why previous attempts to restore vision through electronic implants have not worked so well.
We're using large-scale multi-electrode recordings, and a naive approach would be, and maybe this is why people thought 15 years ago they could do this, is just to implant the massive array of electrodes, fire random signals, see what humans report that they see, and then back that out and have a computer translate a camera into that. There must have been complexity to unpack, and through your work over the decade and collecting the data, you must have not just made correlations, but you must have actually come up with new explanations.
It's really about having a full view of what all the different cell types are and what types of signals each one of them carries. The program that you just described is an interesting concept, that you would just go and stimulate as you will, and then the person tells you what they see, and then you figure it out. The problem is that takes forever when you have thousands of electrodes and thousands of...
There are too many permutations and combinations.
Exactly, precisely. So you can't really do it that way. The other way that people have tried to do it is say, well, let's just pretend that the retina is simply a grid of pixels. Let's just, like a camera. And let's just treat it like a camera. And so when we capture an image from the outside world, let's just pass current through this electrode in proportion to these pixels in the incoming image.
But it hasn't
That
worked.
doesn't work because there's all these different cell types doing all these different things, and you have to control them separately if you want to reproduce the natural neural code.
Whereas in a camera, each cell does the same thing. All of those CCDs are identical.
Exactly.
In the brain retina, we have 5, 6, how many different cells?
20 different ganglion cell types sending 20 different types of visual information to dozens of different targets in the brain. And so you have to reproduce that. The metaphor I like to use sometimes is like an orchestra trying to play a symphony. You have different instruments, they need to syncopate and work together in a certain way, and you have to organize how they work and all that. If you just go in there and just charge ahead with the score and paying no attention to which instrument is playing what, you can do something, but you're not going to call it, the symphony that you're interested in hearing. The science of the retina has advanced to the point where we deeply get it about what all these different cell types are, and my lab has definitely contributed to advancing the ball on that. I don't want to make it sound like we're the only ones, not at all. We're building on the shoulders of giants, but we have a way better understanding. In fact, what has happened in the last 2 or 3 years, literally, is that we have seen a whole bunch of new cell types in the retina that we haven't even figured out yet, to be quite clear. We know something like 5 or 7 of the primary ones, and we know how to dial in the patterns of activity in cells like those. There's another 15 or so that we've just discovered in the last few years, which we're going to need to work on. I think what's interesting there is that we think we can achieve a lot by dialing in the patterns of activity in, let's call it 5 or 7 types, but that doesn't mean we're done. That's device version 1.0 that dials in those patterns of activity. Version 2.0 will require additional research. And I think this is where I want to emphasize that it's an ongoing kind of escalator of research and development. The research needs to be several years ahead. Our understanding of what's going on, we're figuring this stuff out. 5 years later, we got to hand that off to the people who are building something to interface with it. And
in all of these 3 areas, the timing, the spatial positioning, and the types of cells.
Yep.
And I love that metaphor of understanding those allows you to make the orchestra play together in a way that ultimately delivers an image.
Yes, and we hope first instantiation, maybe it'll look like chamber music rather than a full orchestra. But still, the different instruments will be doing their things properly. And that's what I think we can genuinely contribute. In fact, it shocked me when I first found out that excellent researchers who worked really hard to develop the first generation of these implants and did amazing things, by the way, weren't using the information about the basic science that was emerging. And for me, as a retinal researcher, I was frustrated. I was like, well, wait a second, we know all this stuff about how the retina is working, but the engineers over there don't necessarily know about that or focus on other things. We have to bring the science together with the engineering.
And to bring it back to Stanford, that's something Stanford wins at, is bringing science together with engineering.
I think so. Events like BrainMind are important because when you're trying to solve a problem about interfacing to the brain, it's a really interdisciplinary venture. And it involves many disciplines of science, but it also involves people who show up with ideas and ability to transform things, entrepreneurs, investors, people like that, who can see that this particular area of science or engineering is the future, and who can see that if they get involved early, they're going to really have a transformative effect on how things go. And we really need to put those people together with the scientists who are working hard to figure out what that future looks like if we really want to advance these things beyond just straightforward stuff that's standard and available in the marketplace, stuff that's really looking toward the future, stuff that's going to transform the way things are down the line.